Unfortunately, I cannot be here live with you today, but here are the results of the last year of our project on precision irrigation in nurseries. As you all know, irrigation is critical in the nursery. If you don't give enough water, the plant will not reach its full potential. And on the opposite, if you give too much water to the plant, then the roots will lack oxygen and the quality of the plant will be reduced. More than that, the resources are more and more limited, either because of severe droughts that are more frequent than before, or because of restriction from municipalities. Irrigation results often in significant water loss, meaning it's not used by the plant. So you can have overwatering and leaching. You can also have water not reaching the pots when you use overhead sprinklers. And you also have water that is lost when the water evaporates at the surface of the soil or the leaf because of sun and wind. So precision irrigation is allowed to reduce those losses, and we looked at several strategies with our project. So the three objectives of the project were to optimize irrigation management using wireless tensiometer, establish the best clustering practices, and the third one was to compare different strategies for the automation of irrigation. So for this year, we worked on the objective 2 and 3s. So let's start with the first objective, which was to improving clustering. Because there are so much diversity in nurseries in terms of species and cultivars, plants are often grouped together on the same nursery bed and therefore receive the same amount of water. Now, the question is how to group them based on their water needs. And the objective was therefore to identify the best clustering for 25 new species of shrubs and perennials based on 8 previously characterized species. And when I say 25 new species, it's because in the previous year, we did a lot more of those species. And in total for the entire project, we are now close to 100 species. So we can really establish a good chart about how to do the clustering with those species. So here is the list of the 8 reference species that were chosen based on their difference in terms of water need. 4 of them were shrubs and 4 were common perennials. So in that list, you see Salix, Hydrangea, Spirea, Emerocallis. So really different type of need in terms of water. In the previous season, we analyzed over 75 species, and with the 25 new ones, we are covering a wide range of species grown in Canada, like I said just earlier. And here is the list of the shrubs in this year experiments. And you can see it goes from small plants to trees, so really diverse there. The same diversity can be found in the perennial list, with, for example, grasses, shade-loving plants, and full-sun showstopper plants. So really diverse, again, with all those perennials. And with that, we knew we could have really a lot of differences in terms of water need. So the experimental setup was at Laval University Nursery under tunnel, so we could have no rain. So we use wireless tensiometer from Ortho, 2-gallon pots with bark-based soil mix from Fafard, so it is AgroMix N7. We had automatic valves that were connected to the tensiometer hub. So this is also from Ortho. We had water meter that were measuring all the water used in the experiments and micro sprinklers for the watering. So each plant would be water individually, which was needed for that type of experiment. So most of you know what is a tensiometer, but for those of you that are less familiar with the instrument, it's a tube full of water, and this is what we can see here. And at the end of that tube, there's a porous tip. You can see it here with the ceramic white that we have here, and the water is able to go in and out of that ceramic. So when the soil is dry, the water is pulled out of the tube, and the soil tension creates a vacuum at the top of the tube, measured by a gauge. That tension is a good way of measuring the water available to the plant. So here you can see when the soil is saturated in water, the tension is near 0. And when the soil is getting drier, the tension increase. So it can, in that example, at minus 12 for that soil, it becomes to be really dry and the plant is having more trouble to get that water. On this picture, you can see a micro sprinkler. So this is what we use to water the plant. And you can also see the end of the tensiometer. The tensiometer is hidden below the soil surface. And we do that to avoid the sun hitting that top part and kind of changing the pressure inside the tensiometer. So it's really important to place it well. And if you need more information about how to place the tensiometer in a pot, just email us or contact the company that do the tensiometer, and they will provide good information on that. So once a tension is recorded by the gauge here, it goes up to the hub. This is what we see here with the solar panel. And you can see here that the same hub is connected to 8 tensiometers, and it can also be used to control automatic valves. So on those different outlets here, you can connect either valve, automatic valves, or tensiometer. So it's a really good instrument to work with. And the hub sends the information by cell waves, and the data is available on the web interface or on the app on your cell phone. And you can see screenshots of what you can have on that web interface. You can see all the different tension in the soil. You can also set up the exact threshold at which you want the irrigation to start and for how long you want it to be. So it can be really precise. You can do that from far away. So even if you're not close to the nursery, you can do that. So it's a really interesting tool to have there. So under the tunnel, we had our reference species that were controlling the irrigation of all the other species in the same line. So here you can see a line, there's a reference species there. And once the threshold is reached for that plant, then the entire line is watered. So it allows us to see what is the best clustering for all those species that we were looking at. On this graph, you can see the average water provided by each reference species during the season. So you can see that Salix is the one that needed the most water and therefore was watering the most the plant in clustering width. And on the opposite, Tuya was not needing a lot of water and was providing the less with the plant that were clustered with. So we were quite happy that it was really distinct of water range. That's what we were expecting and hoping for, and that's what we got there. So what happened with the species cluster with those reference species? If they don't receive enough water, they will simply die. This is what we get here. So depending on the tolerance of those species to drought, they will either survive in that growth or completely die. And in that other part here, the plant will survive, but won't be at its full potential. So here, as soon as you increase the water, the growth will resume and you will get a bigger plant. So in that area, the more you increase the water, the more growth you get. And then you get to a part where it's a plateau. So basically, if you had more water, you will not get more growth. So you basically give everything that a plant needs and even more if you go on your right. So we try to go in that region. This is the optimum. So this is the minimum amount of water you need to get the full potential of the plant. If you go too far on your right and you apply too much water, then you will have some trouble with your root system and you will reduce the biomass there, so to reduce the growth of the plant. And you can reduce the effect of too much water by choosing a good soil with air circulation in it. This is why you have soil that are really specific to nursery production. You can prevent that decrease in several species by using those soil, or at least increase the range of the plateau. So you can also get a longer plateau with a good soil. And this is why we didn't see a lot of plants dying, even if we applied more water than needed in our experiments. So this is why choosing a good soil is so important. So now let's look at a few examples that illustrates what we saw in the clustering experiments for last summer. In the first one, we see that Russian olive show exactly what we just talked about. So you can really see the shape of the curve that we expect. The species was smaller and had damages with Tuya and Hemerocalis here. You see it's a lot smaller than the other one. There was a plateau when reaching panicum. This is what we see here. So this is therefore the best species to do the clustering with because it uses a lot less water than if you use, for example, Salix. So Salix give exactly the same dry weight. So this is what we see here. It's all equal there. But you can see that panicum is needing half the water than Salix will give. So that clustering here is a lot better than this clustering here. With Cerberus, we see the same tendency, but there was a decrease in size with Salix. So we are in that zone where that plant doesn't like to have too much water, so the growth will start to go down if you give too much water. So here the maximum size was with Rudbeckia here. So this is really the top here. We can see it here also. But there were not a big difference if we do the clustering with Spirea here. And you can see it with the picture. They are really similar between Rudbeckia and Spirea. But there's less water used here with that species. So the best clustering in terms of reducing the amount of water would be this one. But if we really want to go to the maximum size, then I would go probably more with Rudbeckia. With poplar, a species that grows really quickly, the Salix was providing the best clustering. And you can see it here, poplar becomes a big plant really quickly. So this is a 2-gallon pots. And in one season, it can reach several feet high. So in that case, we really see that we are still in that really initial phase that we give more water and you get bigger plants. So we don't know if we have reached the plateau here. And it's not impossible that more water would result in even better growth. But from the information we have, and because Salix is already a plant that needs a lot of water, we believe it's still a really good association here. On the opposite, with the Asta, we are in the plateau for all the species. So you can see here, there's no difference at all. And the pairing with Tuya is the best option in that case. This is not surprising as another Asta cultivar was giving a similar result in the previous years, showing that while we can see differences between cultivars, cultivar within a species will generally tend to react the same way. So in that case, we would use that pairing here that would need a lot less water than, for example, if we use with another shade plants perennial with the astilbe, then we would lose a lot of water for nothing. The last example that I want to give you is Elenium. Elenium gives an interesting example of appearance differences regardless of the biomass. So if we just look here, we can see that there's a plateau here, and this is another way of showing it. So in theory, we could say, oh, panicum would be a good species to do the clustering with. But if we look at the plant in itself, if we look at the appearance, you can see here that this plant is not the same as this one. So what happened is that there were not enough water with those 3 species here to really help the development of the flower buds. So the plant was still growing, producing a lot of leaves and stem, but the flower buds were limited in their development, and they were just falling. So to get really the full development of the plant and get really good appearance, we would need to use the astilbe here. So when we did the clustering, we always looked at the appearance of the plant, also more on top of the weight and the biomass. So this is something to consider. It doesn't happen often. So in most species, the growth will be associated with the appearance of the plant. But in some species like Elenium, you really have a big difference if you don't give enough water in terms of flowering. So the takeaways from this objective is that optimal clustering leads to significant reduction in water use and plants with a better appearance. Generally speaking, the speed of growth and the size of the plant is a good way to cluster species together, although there was many exceptions, and that's why we will provide a chart in the final report that will help in the decision process. Another thing I should point out is the influence of the plug size on and vigor on the experiment that we did. So we saw differences between years with the reference species based on their initial vigor of the plug. And for example, this year, the Rudbeckia were smaller than the previous year in terms of plug size. And vigor, and we saw some kind of a delay in terms of growth that were kind of changing a little bit the pattern of water need during the season. So growers need to evaluate how vigorous their plants are if they want to use them as reference species with tensiometers, and make sure they are the same from year if they always want to use the same one. The second objective for this year was optimizing the automation strategies. The experimental setup was in a commercial nursery with wireless tensiometer, a weather station connected to the web interface, water meters, automatic valves connected to the hubs, and we used two species in clustering, so Salix and Zervilla. And we used the same soil mix, but with overhead sprinklers instead of micro sprinklers. The first irrigation treatment was fully automated irrigation controlled by tensiometer. In this treatment, the irrigation started automatically when the tension threshold is reached. And in the second treatment, the weather station predicted what was the evapotranspiration for the day. And we use a coefficient that the irrigation duration was scheduled each evening to replenish the water that was lost. So in that case, that was really based on how much water we thought the plant was losing every day. And the last two treatments were also based on evapotranspiration, but this time it was by predicting the coefficient with previous data and without correcting it with tensiometer or visual cues. So the difference between this one and those two here, it was really because we didn't use instrument in those one here to set up the coefficient. And in that case here, we use instrument to really make sure our coefficient was good. So how is an evapotranspiration works? How can we predict the amount of water that is lost? Well, it's pretty simple, although the equation itself is not that simple. So you will have a weather station that will collect the temperature, wind, solar radiation, and relative humidity. And the web interface and the software behind it will take those data, put them in a formula, and gives the predicted evapotranspiration. And now most of the weather station will give you evapotranspiration data. So the evapotranspiration is based on alfalfa, so quite far from nursery plants in pots. So we therefore need to adjust with the coefficient. And that's what you will see with the KC. This is the name of the coefficient. Since the plants are growing, the coefficient will increase significantly during the season. So it will go, for example, from 0.5 up to 2 or 3. And let's look at an example of how we can use that to decide how long we're going to water every day. So here is the evapotranspiration for a specific day. It was 4 millimeter. Meaning you would need to apply 4 millimeter of water to replace the water lost by alfalfa. Since we are not working with alfalfa, but in this case we were working with Salix, our coefficient was of 2, meaning that we need to apply twice the amount of water, so 8 millimeter, to replace that water lost. By knowing how much your sprinklers are providing per minute, and you can use bucket to calculate at different places on your bed. So knowing that that your sprinklers are providing, for example, X amount of millimeter per minute, you can know exactly how much time is needed to replace the water lost during the day. In this case, the automatic watering was set to 20 minutes at night to provide 8 millimeter of water. So let's look at the result now. Here we can see the dry weight for the two species, and there were no differences in terms of growth for both of species. However, when we look at the amount of water that was used, there was a big difference. So in that case, you see here in blue, those are two models. And those, the two models were not really working as well as we were hoping for. So while not impossible to get to those prediction and those good curve, more tests would be needed, and our observation seems to indicate that the coefficient could vary a lot between location and based on the vigor of the plant. So example of things that could influence the coefficient are the type of sprinkler used, the amount of fertilizer used during the season and how it is applied, and the type of soil and membrane beneath the pot. So it's really hard to determine a universal coefficient curve for a species. And we don't think it's a really, it's a way that will work a lot with growers. So we think it's probably better to go with another approach and not use those estimate in terms of coefficient curve. Because we see here with evapotranspiration that it can be really highly efficient. So in that case, it was even better than tensiometer this year. Why was it even better than tensiometer? The reason is pretty simple. It is in the case of tensiometer, the irrigation was set to start when the threshold was reached, regardless of the time of the day. And we know that more water is lost at noon than at night. So that's probably why we see a difference between those two here. So both of them did work really, really well. But both of them bring different advantages. So in the case of evapotranspiration here, the coefficient was adjusted throughout the season using tensiometers, explaining the more precise result. But we could also get an experienced grower that could, in theory, use his experience to adjust it every day or every 2 or 3 days by visual cues or by weighting the plants regularly after the watering, just to see if the watering was enough. Based on several years of experiments, we really think that those two options here are really, really good, but they bring different advantages. So what are the takeaways from that part? So full automation by tensiometer is by far the most simple to use. The threshold, it doesn't change during the year, and it necessitates the less time to set it up. So really easy and reliable way to do the watering and do full automation. It is a more expensive approach because you would need all those equipment, but it could reduce water use significantly by combining it to good clustering of species. The evapotranspiration is also highly efficient to reduce water use, and it's a great tool to use with less investments to start with. All you need is a weather station and either tensiometer or an experienced grower to adjust the coefficient throughout the season. The coefficient must, however, be adjusted at least every week and sometimes several times during the week. So the growers need to be aware of the time needed. So it's a good tool, but you need to get used to do those adjustments during the seasons. Once the coefficient is established, the calculus is really simple and can be done easily with Excel, and we will be able to help with that in the final report. So if we look at the highlight of the entire project, we were able to find the best clustering for nearly 100 species, and the entire chart will be available in the final report. Full automation with wireless tensiometer allows managing water efficiently and could be of great help with the labor shortage. And this is where I think it could really help with companies that have trouble to get enough people to work on watering. This could be really a good option. And evapotranspiration is also a great tool to help decide how much water to apply, although it necessitates more monitoring than full automation with wireless tensiometer. And with that, we hope our project will help you find the best solution to help you reduce water use based on the specific of each of your enterprise. And don't hesitate to contact us to get more details. I want to thank all the partners. You were essential for this project, and we are so grateful for your help throughout the different season. Thank you all, and Jonathan, the research associate that conducted the experiments, will be there to answer your question. Bye.
Okay, great. Thank you, Charles and Jonathan. Jonathan is a research associate with Charles, and if anyone has any questions, I think we have time for one.
I have a question. Jonathan, what is your recommendation point for irrigation?
I'm sorry, I didn't get the question.
What are your recommendations regarding the set when you start the irrigation and when you stop the irrigation? What are your kilopascal for irrigation?
We didn't. The kilopascal for the threshold for irrigation depended on each reference species. So in the previous years, we have monitored the optimal threshold for each of the reference species that we used for this project, and therefore it varies between the species. For example, for Salix, it was -4 kilopascal, the best number, but for Emerocallis, it was -12.
Right.